This recording is for Primary Math 4. It's Challenging Word Problems, pages 10 through 18. Page 10 starts with number 3. There are 30 red pens, 45 blue pens, and 75 black pens. They have to be packed into boxes so that each box has the same number of pens. What it isn't clear from on this particular problem, and usually they're very good about being clear, is that they want the same number of red and blue and black pens in each box, not just the same total number of pens in each box. I can tell that because you can see the answer in the back, and also it talks about the hint at the bottom there. It says, see worked example 1. So I'm going to draw a graph to show us how to work that. What we're basically finding here is how many possible boxes I could use. For example, I could put one red pen in each box, and let's do this. There are 30 pens total in the reds, there are 45 total blue pens, and there are 75 total black pens. So I could put the reds in ones and have 30 boxes, or I could put the reds in twos or threes, 5 and 6, 10 and 15 and 30. Those are the ways that I could arrange the red pens into boxes. Now notice I just found the factors. 1 times 30 is 30. 2 times 15 is 30. 3 times 10 is 30. And 5 times 6 is 30. If I do the same thing with the blue, the factors of 45 are 1 and 45, 3 and 15, and 5 and 9. Black is 75. The factors of 75 are 1 times 75, 3 times 25, and 5 times 15. So the possible number of boxes that I could put them in, let's see if I can make it color work. One box would work. I could put them all in one, and they'd have, it's kind of silly to have it in one box because they'd all have the same number of pens, but they'd all be in one box. I could use 3 boxes, and I'd have 10 red and 15 blue, and 25 black pens in each of the 3 boxes. I could use 5 boxes, or I could use 15 boxes. Those are the numbers that they all can go into. So part A, the answer is that I could use 1 or 3, 5 or 15 boxes. And part B, what is the greatest possible number of boxes, would be 15 boxes. You could put them in as many as 15 boxes and have them all have the same number of red pens and the same number of blue pens and the same number of black pens. Number 4. We're told that every group of 10 students shared a big plate of fried noodles, and every group of 8 students shared a big plate of salad. And then we are told that a total of 9 plates of fried noodles and salad were used. How many students were there? This just begs for a chart. This is, again, we're starting off the year with several opportunities to draw a chart and have an informed guess and check. We're not just throwing numbers out there, but we're having some sort of a guess and check for it. We have noodles, we have salad, and we have the total number of meals that the students are going to eat. Now, our students, first thing we have to realize is we have to have the right number of students. For every 10 students shared a plate of noodles, and every 8 students shared a plate of salad, there must be a number that is common that 8 and 10 both go into. In other words, you can't have 15 people there because all of them are sharing the plates, is the way the problem is to be read. So if I find the least common say the word right, the least common multiple of these two numbers. 10 is 2 times 5, 8 is 2 times 2 times 2. So the least common multiple is going to be 2 times 2 times 2 times 5. Again, remember, I have to have the 2 times 5 in there, and I do, and I have to have 2 times 2 times 2 in there, and I do, and so the least common multiple is equal to 40. So I could have 40 students, or I could have 80 students, or I could have 120 students. Now the noodles are shared, 10 students share the noodles, and 8 students share the salad. If I have 10 students sharing every noodle dish, with 40 students, I use 4 noodle dishes. If 8 students share the salad, then I must have 5 students, or 5 salads to share with the 40 students. That gives me a total of 9 noodle and salad dishes, and right there's the answer. A total of 9 plates of noodles and salad were used. How many students were there? The very first option was the best one, and that was that there are 40 students. The hint there is that the total number of students doesn't leave any remainders when divided by 10 and 8. Again, you can't have 15 students. You have to have a number that goes into, that 8 and 10 both go into. So finding the least common multiple is 40 and then trying it, the first one worked. Again, we're always going to write our answers down. We're going to label them well. The question was how many students, and the answer isn't just 40, it's 40 students. Problem number 5 is what we eventually call a Venn diagram, but in the beginning right now we're just studying the diagram to look at the describe the observations. This is the diagram they have in the book, and I even color-coded mine because I want to make sure we understand something about this. Of course, everybody knows that pink and blue make purple, and so I made mine so that we can see that the numbers in the middle in what they're calling Part C are both in Part A and in Part B. So C is not its own category only. Everything in C is made up in A, and everything in C is part of Group B, and then they're also their own little category of Group C. So the question that we're asked for Part A is which of the group contains some factors of 96? Well, if we want to think about the factors of 96, 1 in 96, 2 times 48, 3 times 32, 4 times 24, 6 times 16. Should we go on? I guess we can go on a little bit more. 8 times 12. I believe that's going to be all of them. It is. And so what we see is that Group A includes 1, 2, 3, 8, and 24. Now, it's not all of the factors of 96, but it is some of the factors of 96. So which group contains some factors of 96? And that answer would be Group A. Part B asks the question, which group contains some factors of 60? Well, 60 is 1 times 60, 2 times 30, 3 times 20, 4 times 15, 60 has a lot of factors, 5 times 12, 6 times 10, and that would be all of those. Notice that in Group B, we have 1 and 2 and 3, and we have 15 and 30 and 60. So the answer to question B is that Group B is the one that contains the factors, some of the factors of 60. And then Part C asks, which group would the number 6 go into? Notice that 6 is in this group, and 6 is in this group. So if it's in both of them, then Part C, 6 would go into Group C. The number 6 would go into the purple group because it is both a factor of 96, group A, and a factor of 60, group B, which puts it definitely right there in the intersection of group C. Number 6 talks about a rectangular piece of wood, and I went ahead and drew one, 175 by 150 by 75 high. It's cut exactly into a number of identical cubes, and the question is how many cubes of the greatest possible size can be cut from the pieces of wood. Now, of course, you could cut a bunch of cubes that are 1 by 1 by 1. That'd be a whole bunch of them. But what we're trying to do is to cut the cubes to be the greatest possible size, as big as possible. You say, well, how about I cut it 75 by 75 by 75? Well, that's good, except it has the word exactly. We want to cut it exactly into a number of cubes, which means no waste. Mathematicians are extremely particular about words. So the word exactly is how you know that there's going to be no waste. You're not going to just cut one big thing and be done with it. Greatest possible size means you're looking for one particular answer. There'd be an infinite number of answers that you could have. Maybe not infinite, but a whole bunch of them if you didn't have to do the greatest possible. And you could kind of do infinite if you could do 1 by 1 by 1 centimeter and a half by half by half centimeter and a whatever. Anyway, you could go on quite a bit from there. And then we're trying to figure that out. The answer comes to me pretty quickly because when I look at these, I think about money and dollars and quarters and that every one of these is a multiple of 25. To be sure, you would have to find the factors of each one. But also remember, you could actually start with the 75. 75 is 1 times 75. It's 3 times 25. It is 5 times 15, and that's the only factors. The greatest factor of all of them has to be one of these 6 numbers. Even though 175 will probably have more factors, if it's not in all 3 of the lists, then it can't be the greatest common factor. Okay, and so when I'm looking for that, I can start with the smallest one. I can find those 6. 75 goes into here. That's 2 times 75, but 75 does not go into here evenly, so the biggest possible one doesn't work. 25 is the next option, and clearly 25 is going to go into everything. 150 is 6 25s. Just like $1.50 is 6 quarters. 175 is 7 25s, just like $1.75 is 7 quarters. And this is 3 25s. So I know that my piece of wood is going to be 25 cube centimeters. And the question is, how many can I cut? Well, if I think about how many I can cut, I know it's going to be 3 tall by 6 deep by 7 long. And if I cut this, okay, keep in mind what we're doing is we're saying I can get 7 25s out of the length, I can get 6 25s out of the width, and 3 25s out of the height. So if the cube is 25 cubic centimeters, 6 times 7 times 3 is equal to 126 blocks. I can cut 126 identical blocks that are 25 cubic centimeters in dimension out of that big board. Number 7 is another problem. Most of these are where we're making some sort of a chart, organizing our data into a something we can track and figure out. So Mr. Thomas has some erasers. When he gives 4 or 5 erasers to each student, he has 2 left over. There are no erasers left when he gives 6 erasers to each student. And the question is, what is the least number of erasers that Mr. Thomas could have? If I make a list of 4 erasers, 5 erasers, and 6 erasers for each one. And what I'm trying to do, what I know for sure is the number of erasers he has is a multiple of 6. I know that because there's not a remainder, there's no erasers left when he gives 6 erasers to each student. So we might have 6 or 12 or 18, something along this line. I don't know how many. The question is, if he has 6 erasers and he gives 5 to each student, what he's going to have is 1 left over. If he gives 4 to each student, he's going to have 2 left over. What the problem tells us is that when he gives 4 or 5, he's going to have 2 left over. So I need to find one where both of these numbers are 2. If he has 12 erasers and gives 5 to each student, he does have a remainder of 2. But if he has 4 erasers, he has no remainder. So that one's not our answer. If he has 18 erasers, gives 5 away each, he'll have a remainder of 3, because 3 times 5 is 15, and 18 is 3 above that. But if he gives away 4 erasers, he has a remainder of 2. So I'm not getting anywhere very fast, but as soon as possible, stop and see if you can see a pattern developing. We have 2, 0, 2. I wonder if I'm going to have a 0 on the next one. And sure enough, if I have 24 erasers, if I give 5 out at a time, then I have 4 remaining, and this one goes in 0 times. Now, do you remember we've talked about remainder theory? If you have 5 items, you'll never have a remainder of 5. What happens with 30 erasers is you have a remainder of 0. And this one, not surprisingly, has a remainder of 2. Maybe we can take one itty-bitty shortcut and realize that this one, the next one, is going to have a remainder of 1, while this one has a remainder of 0, and the next one will have a remainder of 2 for both of them. You could check the numbers, and sure enough, it'd be true. If you have 36 erasers, if you give 5 away, you'll have a remainder of 1. If you give 4 to each student, you have nothing remaining. But the very next multiple of 6 is going to be our hooray spot. 42 erasers, given away 5 at a time, has a remainder of 2. Given away 4 at a time also has a remainder of 2. And given away 6 at a time has nothing left over, no remainder. So the answer is the least number of erasers he could have is 42 erasers. Not a hard problem to do mathematically. It's the thinking and the understanding numbers and the patterns and the remainder theory that we're working real hard to grasp. Number 8, some of Mr. Edwards' students want to buy him a gift. If each of them pays $2, they'll be short of $4 for the gift. If everybody pays $3, there's an extra $3. How much does the gift cost? I'll draw a chart. This is how I drew my chart. And I said that there's a number of students, and if the students pay $2, then they're short $4 for the gift. So if I take $2 and I add 4, that's the cost of the gift from one perspective. The other thing that I know is that if I do $3, and this of course is per student, I didn't write that on there, but $3 per student and $2 per student. If I were to have $3 per student, it says I have an extra $3. So that's also another way of talking about the cost of the gift. If I take a number of students and I can find one where both of these match, I'm in good shape. So maybe I start with a really easy number like 10. If I have 10 students, then the cost of the gift would have been $24 figured this way, and would have been $27 figured this other way. Well, that's pretty close, really. Let's see what I would do next. What I don't know, though, from there is if it should go higher or lower. Let's try 5. 5 is an easy number. At $2 a piece, that would be $10 plus 2 is 14. At $5 a piece, that'd be 15 minus 3 is 12. Notice what happened. I did have 24 was the lower number. Of the two numbers, 24 was lowest, And of these two numbers, 12 is the lowest. What that tells me is that my answer is somewhere in between those two numbers. At first, the $2 number was too high. By the time I got down to 5, the $12 number was too high. I'm sorry, I said it backwards. It was too low. They have to be balanced. It has to be the same thing. So I'm going to try in the middle. Let's try 7. $2 a piece is 14 plus 4 is $18. $3 a piece is 21. Subtract 3, and look at that. We get $18. So based on this, I must have 7 students, but the question actually is, how much does the gift cost? The gift must cost $18. And by the way, we also know, something else I didn't ask us, is that there are 7 students in the class. That's the only number that is going to work to make the cost of the gift the same if you have each student pay $2 and you come up with $4 more to make up the difference, or you have each student pay $3 and you take the 3 off their extra. Some sort of a chart. Your child's chart may look different than mine. If they can't find a way to organize their data, help them find a way to organize their data so that they can solve the problem. Number 9, lots of words. Students were selected from a school's 4th grade class to take part in a science contest and a spelling contest. So we have a science going on and a spelling contest going on. From one class, 9 students were selected for the science contest, and 3 were selected for the spelling contest. Now we're looking at 4th grade classes, and this is one class. There's more than one 4th grade class. It tells us that in the beginning. For each of the remaining classes, everybody else has 4 for science and 6 for spelling. When it was all said and done, the number of students who were selected to take part in both contests is the same. What is the smallest possible number of 4th grade classes? Well, one easy way to do this is to continue adding. At this point, we have 13 students and 9 students. I know they're supposed to be the same number. It tells us that the number of students selected to take part in both contests is the same. And every other class adds a total of 4 for the science and 6 for the spelling. So we could just keep adding this up until we get to a number that is the same. And there is nothing wrong with that. And we find out that at 21, they both even out. The smallest possible number of 4th grade classes, this is the first class, this is the second class, and the third one, and the 4th one. There are, the smallest possible number of 4th grade classes is 4. Now, you could also realize that we have a difference of 6 between the two right now. Every time we do this, the difference is going to go down 2 because 6 is 2 more than 4. So you could have stopped and realized that a difference of 6 that has to be made up 2 at a time is going to take 3 more steps to make it up. And so if this is the first class, then the second and third and 4th classes will have to be added in order to make them all the same. Problem number 10, we have a group of 4 students visiting the Smithsonian. Some of the students took taxis and 3 took a subway from the hotel. And each taxi carried 4 students. So we had 3 on the subway. Let's do a from and to. This is from the hotel. And then we have another one that goes back to the hotel. And what we know is that there are 3 students on the subway. And the taxi on the way to the, or from the hotel, the taxi carried Each taxi carried 4 students. So we don't know if there were 4 or 8, 12, 16. We don't know how many students there were, but we know the people in the taxi were a multiple of 4, and we know the people in the subway were exactly 3. When they were coming back, the subway had 8 students riding it, and the taxi, each taxi carried 3 students. Multiples of 3. Now, the number of taxis and the number of students were the same for both trips. If there are 5 taxis one way, there are 5 taxis the other. And of course, the students going from and to the hotel needed to be the same. You don't want to lose anybody. So if I were to combine these, I'm just going to add 3 to each of these. The total number of students could have been 7, 11, 15. I should have left a little more room for this, but that's all right. 19, 23. Let's see if I have a winner yet. I could have had 11, 14, 17, 20, and 23. If I had 11 students, I would have had 2 taxis. Here, I could have had 11 students, but I would have only had 1 taxi. So it looks good in the beginning, but that matching number doesn't work because I have to have the same number of students and the same number of taxis. 23 is my next option. This is 5 taxis and a total of 23 students. 1, 2, 3, 4. Yep, sure enough, 5 taxis and 23 students. The question is, how many students and how many taxis are there? And we have found that there are 5 taxis and 23 students. We are not really learning a lot of math skills here. We're using multiples a lot. But the point of this section in your book to begin with is to start helping our kids think through things logically, clearly, carefully. They may need a lot of guidance in learning that skill, and that's okay. It's a good skill to learn. Problem number 11. A whole number greater than 11 gives the same non-zero remainder when divided by 3, 5, 7, or 11. I hope that those words are beginning to mean something to you and have the keywords jump out at you. If it's a non-zero remainder, then it is a multiple of those numbers. That's what a non-zero remainder means. Okay, and the smallest value is going to be the least common multiple. Now, each of these are prime numbers, 1 times 3, 1 times 5, 1 times 7, 1 times 11. So the least common multiple is simply going to be 3 times 5 times 7 times 11. The least common multiple is 1,155. Now, let's go back and read the questions. A whole number greater than 11 gives the same non-zero remainder when divided by 3, 5, 7, or 11. And I actually read that wrong a while ago. I apologize. To find one that has a non-zero number, the same non-zero remainder, then we had to first find the one. This is the first number that gives a remainder of 0. Because it's a common multiple, it gives a remainder of 0. If you want the same non-zero remainder, and the smallest number possible would have to be 1,156, because that's going to have a remainder of 1 for each of those, for 3 and 5 and 7 and 11. 1,155 is the least common multiple. It's the first number they all go into evenly. If they have to have the same remainder, then you've got to start with the first number that they're all go into evenly and go up from there. And the smallest remainder you can get, of course, is 1. Not a hard problem if you can understand all the pieces that it's asking. Number 12, I always told my children who are doing these, just because one seems hard, don't skip the rest of them, because really, this one's a fairly simple problem. List all the 4-digit numbers which can be formed from the digits. Each digit can be used only once. How many numbers are there? I would start just making a pattern. If I start with a 9, it doesn't matter actually, let's just do it like in the order that gives it to us. If I start with a 6 and I go with a 2 next and then I have a 9 and a 0, that's one number. I could do the same thousands and hundreds digits and switch the ones digit. But after that, if I leave these two the same place, I can't make any different number. So I'm going to leave the thousands digit the same and try the 9 in the hundreds place. And then I also have two options. But I could put the 0 in the hundreds place. And I have two options for that as well. What I can find out is it's the same idea if I put the 6 in the thousands place. Then I have three options for the hundreds place. And then I have two choices for the tens place. And by then, at the end of that, there's only one choice for the ones place. It doesn't matter what number I put in front. If I put the 2 in front, if I use the 600, I have two options. If I use the 9 next, I have two options. If I use the 0 next, I have two options. If I put the 9 in front, do you see the pattern that it works out the same? And what's the only limiting factor? I cannot put 0 in front because that is a 3-digit number. A leading 0 doesn't count as a 4-digit number. So what I have is 6 times 3, or 18 possible numbers. How many numbers are there? If you use each digit once, there are 18 numbers. And I've listed them all. Now, once you understand this concept, there's a couple of shortcuts. One of them is the fact that whatever number I have in front, I'm going to have 6 options along with it, and I have 3 numbers to go in front. 6 times 3 is 18. Without even listing all of these, I could have made the logical deduction that there are 6 with a 2 in front and 6 with a 9 in front, giving me a total of 18 numbers. And that's a perfectly fine way to do it. We're going to go ahead and do a page off of the next section, or a couple of pages actually, off of page 17. So this is the next section of word problems in here. We're talking about the 4 operations of whole numbers, but we're just going to go ahead and combine it here for a couple of pages. So number 1 on here, it's reported that there are 873,000 of native speakers of Mandarin Chinese, and there are 178,000 who speak it as a second language. And the question is, how many speakers are there? We're just going to add those together. Lots of ways you can add it. You can simply just go left to right and realize that 8 and 1 is 9, but I'm going to have another 100 from the tens column, so that's 10 hundreds, or 1,000. When I make a 10 out of this, I'm going to give away 3, and I'm going to have 4 still left over here. But notice that in my ones column, I'm also going to make a 10, so that's going to give me 5 tens. And when I make a 10 with the 8 and 3, I have 1 left over. Again, it's much faster to do without saying it all out loud, but I want to show you my way of thinking so you can stretch your mental muscles and get it done quickly and learn how to do that quickly. Now remember, I did the shortcut. This is 873 thousands and 178 thousands. So my answer is 1,051 thousands, which could also be stated as 1,051 thousands. There are 1,051,000 speakers of Mandarin Chinese, according to these numbers. Number 2, Pete has 438 cards. Peter. Pam had another 379 more cards. No, I'm sorry, if sorry, I missed that word. If Pam had another 379, she would have twice as much as Peter. So this would be what it would look like if Peter had another, sorry, get my words right. If Pam had another 379. So her cards must end right there. She doesn't have these. If she did, she'd have a full second box, twice as many as Peter. So the question is, how many cards does Pam have? All right, a couple of things we could do. One is realize that each of these boxes is 439. I'm sorry, 438. If 438 is this whole pink box, then we want to know how much is there in this part of the box that she does have. She doesn't have this, the 379, she does have this, and we could find out how much that is. Now when I subtract this, before I start borrowing, again, I like to go back and think of it as an addition problem. I need 11 to get up to 400, and I need 38 more to get to 438. So if I were to subtract those, I would get 49. But to me, it's a lot easier to go up 11 and up 38 and get 49 out of it. So what that tells me is that Pam has 49 right there. So all told, she has 438 and she has 49. I can think about that as 437 plus 50, which is 487 cards. Now I just got, I think I made a mistake somewhere because I have a different 10 in my answer. Let me pause and find my mistake. Yep, there it is. Talking and writing at the same time is not easy. This would be 21 higher, which would make this a total of 59. And so let's just redo that. If this is 59, then I have 438 plus 59, which would be like having 437 plus 60, which gives me 497, and that does agree with the answer I have in my notes. Problem is when I work it differently on the board than I do in my notes. Here's what I did on the board on my notes the first time around, because there's two ways to do it, right? We could subtract and find this part, or we could do this way. We could say, change colors for the second method. We could say that altogether, Pam has 438 plus 438, and then I would subtract the 379. I know that each of these is 438, but she doesn't have that last 379. And so, again, I can do it however. I could add this together and have 876, and then subtract 379. If I'm doing that mentally, I'm going to subtract 376. Again, I wouldn't write all this down, but just so you can get a window into what I'm doing. If I wanted to take away 379, I could take away 376 and then take 3 more away, and look how easy that is. That's an even 500. Take 3 more away, and I have 497. But again, all of this I can do in a flash in my head and come down with 497, especially if I'm not talking and writing at the same time. Either way, 497 cards is the correct answer. Number 3, the sum of two numbers is 1200. Their difference is 214. So if I put the two numbers together, I get 1200. The difference is 214. What are the two numbers? And the hint says to solve it in more than one way. Again, this is exactly the same idea. I could, maybe the most obvious option is to take 1200, subtract this 214. Okay, think about it a second. If you have 1200 and you subtract 200, you're at an even 1000. If I subtract 14 more, I would be at 986. 986 would be the combined amount of those two boxes. Remember, I started with 1,200. I got rid of the 214. 986 divided by 2 would be, can you think that through without writing it down? That's 800 and 186. Maybe you could say that is 400 twos and 93 twos. So that would be 493 for each one. So the two numbers, one number is 493, the other number is going to be 707. That's when I added 493 plus 214 and got 707. What's the other way to do it? If I have two numbers that are a total of 1,200 and the difference between them is 214, it might be even easier. It's a little less obvious to us, but instead of subtracting, what if I add 214? Now I have a total of 1,200 plus 214. That's pretty easy to do. It's 1,414. If I divide that by 2, again, pretty obvious to say that's 707. That's the entire box that I've gotten. That's 707 for this whole thing. But this piece doesn't have the 214. 707, take away 207, gives me 500, and I take away 7 more and get 493. So that would tell me that this box is 493. We have to make the two boxes equal. I can either make it equal by subtracting 214, and that makes both of them the smaller size, or I can make them equal by adding 214, and that makes both boxes the large side. Either way, I find one of the numbers, and I have to solve for the other one. If I do it on the right side, I find the 707 and I solve for 493. On the left side, I find the 493 and solve for 707. Number 4. Draw it up before I write it down. I can't draw apples and lemons well enough to try it, but I can at least color code it. We'll call that red apples and yellow lemons. What I'm told in problem number 4 is that I have 4 apples and 7 lemons, and it cost $47. Now I know that each apple costs $2 less than a lemon, and we're trying to find the cost of 3 lemons. Here's the point. My sizes currently, my prices are not the same. I can't take that 47 and divide it by 11 because there's 11 pieces of fruit there, because the prices are not the same. But if the apples are $2 less than the lemons, if I added $2 to the price of each apple, then I would have equal groups. Can you think about the fact that the price for everything in a purple box is now the same? Because I added $2 for the price of an apple, and now every purple box represents the same thing. But if I add $2 for the price of an apple, it's not equal to 47 anymore. It has to be equal to 8 more than that. So now it would be equal to 47 and 8 is going to be $55. When I have that, all of my boxes are the same, and there are 11 boxes. If I have $55 divided by 11 groups, it's $5 per group. What that tells me is that each of my purple boxes is $5. A lemon is $5. An apple was $3, but then of course when you add the 2, you get 5, and that makes it the equal group. Now the question is, what is the cost of 3 lemons? If 1 lemon is $5, then I know that 3 lemons would cost $15. Now, this is the beginning. Again, you are really baby steps into seeing how an algebra problem works, how an algebra problem is solved, but it's meant to be extremely tangible here, to be able to take this information and realize that I can't divide them into 11 groups because I don't have 11 of the same thing. But by adding 2 to the apples, then the price of the apple and the price of the lemon is the same, and instead of it adding up to $47, it would add up to $55, which works out into an even dividing of 11. Might take a few times, a little bit of thinking for that to really sink in. And again, there are other pictures in the back of the book that are drawn a little bit differently. They're great. Use those too. Vince and Zach collected a total of 952 stickers, and Vince collected 3 times the number of stickers that Zach collected. And these guys have 952 stickers. Jason collected half as many as Zach. So he has half of a box. And we're trying to find out how many stickers each one collected. All right, if I have these stickers, the 2 guys have 952, and they're divided into 4 equal groups, that ought to be pretty obvious at this point. I'm going to divide it by 4. Again, I keep doing it the mental math way, and I'm writing it all out. I wouldn't necessarily write it out and doing it mentally in my head, because that's how you do mental math. But when I'm writing it out for you, I'm showing you how I think about it. 900 is 800 and 152, and the 800s, if I divide it into 4, I get 2 hundreds. 152, I could call that 12 tens, and 12 tens divided by 4 is 3 tens, and that leaves me with 32 ones, which divides by 4 and gives me 8 ones. So I have 238 for each of these boxes. And the question is, how many stickers did each person collect? So Zach has 238 stickers. J is Jason. Jason had half of that many, so that would be 119 stickers. Again, a little mental math there. Vince has 3 of these. 238 times 3 is going to be 690 and 24. 714 stickers is what Vince has. Number 6. Tripods have 3 legs. Bipods have 2 legs. We have some tripods and some bipods that have 15 legs altogether. What are the possible numbers of tripods and bipods? Sounds like a tongue twister more than a math problem. Let me make a table, and I'll turn it back on when I get it done. I think sometimes it's hard to know how to organize information. A way that I organize it that makes sense in my head may look very different than the way you would organize it. This is one suggestion. It's not the only way to do it, certainly. But it occurs to me, if I want 15 legs total, I could have 5 tripods, and that would give me 15 total legs, and I would have 0 bipods with 0 legs for the bipods, and I would have a total of 15 legs. Notice, by the way, this is the total number of legs, I guess I should say, like that. So the most tripods I could have would be 5. As far as bipods go, 8 would be too many. 8 bipods would be 16 legs, and it doesn't work, but that's just barely too many. So I have somewhere between 5 is the most and 1 is the least, and 8 is the most and 0 is the least. I probably would work on this side just because I only have 4 more options, right? So if I have, and by the way, this would not be an option as an answer, because it does say that you have to have tripods and bipods. So having all tripods is not an option. It does work, but it's not an option. It does not work to have all bipods, because if I had 7 bipods, it'd be 14 legs. That still doesn't work. If I have 4 tripods, Then 4 times 3 is 12. That'd be a total of 12 legs. I need to have 3 legs in the bipods, and I can't do that. Remember, bipods have 2 legs each, so I cannot have that, and that one will not work. If I have 3 tripods, there are 9 legs. Remember, my total I'm trying to always make 15. That one doesn't work. If I'm trying to make 15, then I need 6 legs for my bipods, and that means I need 3 bipods, right? Keep up with where the numbers are coming from. 3 bipods means 6 legs. 3 tripods means 9 legs. And that gives me a total of 15 legs, which makes us all very happy. All right, let's continue on. If I have 2 tripods, 2 times 3 is 6. That would be 6 legs. That means I need to have 9 legs in my bipods, and I can't do that because bipods come in pairs. I don't have any pairs. I could have started with 8 and gone down, or I could start with 5 and go down. Since 5 is smaller, I went with that one, and so I don't need all of those checks over there. 1 tripod has 3 legs. That means I need 12 legs from my bipods, which means I need 6 bipods, and that does work to be a total of 15 legs. Again, this is my second option. 1 tripod of 3 legs along with 6 bipods of 12 legs gives me a total of 15 legs, also a very happy answer. The first one is a happy answer, except it doesn't use both of them, and so we're going to consider that not working. The question is, what are the possible number of tripods and bipods? So you could have 3 tripods and 3 bipods, or you could have 1 tripod and 6 bipods. The question doesn't say what is one answer. It says what are the possible options, and all of the options that are listed, or all the options that are possible are listed there.